In the 2014 movie Interstellar, a group of astronauts leave a blighted Earth in search of a new planet that can house the human species. One such planet that they investigate is referred to in the movie as Miller's Planet. This planet orbits closely around the black hole Gargantua. Due to the black hole's gravitational pull, the surface of Miller's Planet is dominated by colossal waves with 610-meter amplitudes. These waves travel at a speed of 18 meters per second and leave a space of 6,480 meters in between their crests. While on the planet, the crew's shuttle is struck by one such wave and is violently flung upwards. We are asked to find the vertical velocity of the crew's ship 1 minute after reaching the crest of the wave. To solve this problem, we will need to use the derivative of this formula for vertical position on a wave from time, frequency, and amplitude. However, this formula requires information about frequency that we do not have. Luckily, the problem gives us values for wave velocity and wavelength, and dividing these values gives us a value of 1 over 360 Hz for frequency. Now, we need to take the derivative of the vertical position equation. In order to avoid having to use the product rule, we can replace the amplitude variable with its value, as we know from the problem that the waves have a constant amplitude of 610 meters. Now we take its derivative and ensure that we chain the constants inside of the cosine. Once this is done, we can plug in our known values for frequency and time. In addition, we know that the change in time over the change in time will be a constant 1, and frequency does not change over time as we were given constant constituent values. So we end up with this expression, which simplifies to a vertical velocity of negative 9.22 meters per second a minute after the wave's crest strikes. During this ordeal, Cooper is focused on something other than the massive wave he is riding. He's wondering how the time dilation caused by the black hole's gravity is affecting the age gap between him and his daughter Murphy, who is still on Earth. Miller's Planet, and consequently Cooper, orbits the black hole at a distance of 2.394 times 10 to the 10th meters, and is pulled towards it at a constant 2.113 times 10 to the 6th meters per second squared while exhibiting centripetal motion. At what rate is Murphy's age changing per hour of Cooper's time? For this problem, we will need the derivative of the time dilation equation. First, however, we need to find the velocity that the planet travels at, so that we have all the information we need for the time dilation equation. We are told that the planet exhibits centripetal motion, which means that its acceleration towards the black hole and radius from the black hole allow for the value of its velocity to be constant. We can solve for this velocity by plugging the other two values into this equation, which gives us a velocity of 2.249 times 10 to the 8th meters per second. To simplify this value, we will put it in terms of c, the speed of light. This gives us a velocity of 75% the speed of light. Now we must take the derivative of the time dilation equation. We can use the quotient rule for this, making sure that we chain the inside of the square root in the denominator when we take its derivative. Then we must solve for the change in Murphy's time over the change in Cooper's time. We can plug in our known value for velocity. In addition, we know that this dt over dt must equal 1. Also, this entire subtracted right side of the equation can be reduced to 0, because we know that the velocity of the planet is constant. We are then left with just this expression, which simplifies to a change of 1.5 hours in Murphy's time for every hour of Cooper's time. Hopefully, they can escape Miller's Planet before this time dilation becomes too severe.